We use software to control all sorts of industrial processes. Whether it's a wastewater treatment plant or a semiconductor fabrication facility, process control is important in many processes to operate efficiently and safely. The most basic form of process control is called a feedback loop. Imagine that you have a simple real-world process to control, a room. In this room, you have a heating vent and a thermostat. Your goal is to provide a comfortable room temperature. A feedback loop has four basic components: a sensor, a controller, an actuator, and the process itself. In this case, the sensor is the thermostat, and the controller is the software. The actuator provides a physical means to manipulate the process. This may also be called an effector. The process is the room itself. Your feedback loop might work something like this. First, the sensor reads the temperature. It's 15 degrees Celsius. That's not very comfortable for the people in the room. The sensor sends this reading to the controller, your software. The software computes the difference between the desired temperature of 21 degrees and the actual temperature, 15 degrees, which of course is 6 degrees difference. The desired temperature is called the set point, while the difference between the set point and the actual value is called the error. Because the temperature is too low, the controller tells the heating vent to open. Now there is hot air going into the room. Eventually, it heats up to 21 degrees, which is the desired temperature. Now the thermostat reads 21 degrees. The controller compares this to the set point and finds no difference, no error, so it tells the heating vent to close. Now, no more hot air is flowing into the room, so the temperature does not rise anymore. The vent will remain closed until the temperature falls below 21 degrees. From a software point of view, the controller logic must run continuously. It is not only run once, but many times, because the process is always changing. The temperature of the room must always be checked to see if it is still at the set point. The frequency, or how often the loop runs, depends on the desired level of control and the sensitivity of the system. For example, controlling a self-driving car has much tighter timing constraints than controlling a room's temperature. The temperature of a room is also much slower to change than many processes, so checking it every microsecond is not necessary or useful. At their heart, every feedback loop follows a similar form to the example above, but there are ways to improve. In the example above, the heating vent can only be open or closed. This leads to a problem. If the heating vent is wide open, too much heat will be added to the room before the thermostat detects it, because the hot air takes time to mix into the room. The occupants will be uncomfortable again, because now it's too hot. Let's make an improvement. Now, our heating vent can be 0% open or 100% open, or anything in between. The controller reads the error and opens the vent according to how big the error signal is. Now, when you are close to the set point, the heating will slow down, so that you can approach the set point gradually. This is called a proportional controller, because the amount the vent is open is proportional to the difference between the set point and the actual temperature. For reasons that are outside the scope of this course, proportional controllers also have undesirable effects, so there are improvements to them. The basic concept remains the same though. The software compares a measured value, like temperature, to a set point, like desired temperature, and controls the process to get the desired result. Other variations on process control exist as well. A feedback loop is an example of a closed loop, because information from the process is used to control the same process. An open loop refers to a process that is controlled without monitoring the process. It is simple, but cannot deal with changes in the process. It also cannot check itself to see if it's actually succeeding. Older clothes dryers are an example of open loop control. You simply put the clothes in, and the dryer runs for a set amount of time. Feed-forward control occurs in systems where there are processes in series. Information from an upstream process can be used to control a downstream process. This allows for a coordinated, proactive response, but it requires a very good model of how the process responds and will not deal with unknown events very well. Feed-forward systems are often used in conjunction with feedback loops, as we can see here. For example, you could implement feed-forward control in a flood protection system for a town. Suppose an upstream monitoring station detects large flow rates. This signals the controller for the town system. The controller in turn asks the actuator, a gate, to open and divert some water into a reservoir to keep water levels low. This feed-forward system could work on its own, or work alongside a feedback system for controlling the water level. In our room temperature example, the software architecture would be very simple. The software must simply turn one input into one output, so this could be a pipe and filter architecture. More complex problems may have many sensors and many ways to control the process. Think about a self-driving car. It must take information from all kinds of sensors like radar, LiDAR, and cameras. It can also control itself in several ways that are not separate from each other. throttle, brakes, and steering. The process control architecture for a complex problem like this is much more complex, but it usually looks something like this. This architecture is based on a MAPE case structure. It comprises 4 major steps: monitor, analyze, plan, and execute, and all 4 of these steps must have knowledge of the process. The first responsibility is to monitor. This is the component or collection of components that interface with sensors, turning their raw signals into meaningful information for the software. Next, the software must analyze this data. This can be much more sophisticated than in the room temperature example. It could integrate data from several sensors and build a complete picture of how the process is behaving. More sophistication generally requires a better model of the process. The next step is to plan. Like analysis, more advanced planning needs will require more knowledge. Your software will have to know how the process will respond before deciding how to make the desired change. This knowledge is in the form of a model of the system. Software developers should only build these models in close conjunction with engineers that specialize in the process. Finally, there's execute. After the analyze and plan components have done most of the thinking, the execution components will be relatively simple. At the very least, they will simply turn desired actuator positions into signals to communicate to those actuators. I can't overstate the importance of the knowledge component in complex MAPE case systems such as self-driving cars. Technology companies are investing heavily into such cyber-physical systems. A huge amount of investment goes into extensive real-world testing, machine learning, and data modeling to operate these systems, all underpinned by an effective software architecture. Although process control is often handled by specialized professionals for all but the simplest problems, it helps to be aware of it and when it should be used. Every modern manufacturing operation in the world contains at least simple process control. Even your house or apartment building has feedback loops. With the advent of machine learning and big data, process control is becoming ever more complex, and software is becoming an ever bigger part of controlling physical systems. Opportunities for developers in these fields will continue to grow as more companies realize the potential and the software industry gets better at developing solutions.